There's a computer sitting in a Moscow museum that nobody talks about. It looks ancient, unremarkable even. But here's what makes it terrifying. It was better than anything we use today. More efficient, cheaper to build, simpler to operate. And it worked on principles that could have saved billions of dollars in energy costs right now.
So why have most people never heard of it? Because in 1958, the world made a choice. And that choice might have been the biggest mistake in computing history. What happened next is a story of brilliant engineers, Cold War politics, and a technology so revolutionary that it got buried for 70 years. Until now. Because one of the world's biggest tech companies just proved that this dead technology might be humanity's only way forward. And when the details emerge, everything about modern computing starts to look like a beautiful, expensive mistake.
The hidden revolution in every processor. Right now, billions of transistors inside devices around the world are switching on and off. 0, 1, 0, 1. It's been this way for 7 decades. Every computer, every smartphone, every data center on Earth speaks the same language. Binary. 2 states. Nothing more. But here's the uncomfortable truth nobody wants to admit. This might have been a mistake, not a small one either. A fundamental limitation baked into every piece of technology that exists. In 1958, engineers built a computer that didn't use binary at all. They proved it worked better, cost less, and was more efficient. And the only reason most people have never heard about it is because history chose the wrong path. This story gets wild. When the Soviets were winning, picture Moscow in the 1950s. While America was celebrating its technological supremacy, Soviet engineers were quietly building some of the world's most advanced computers. They created the BESM-1, a machine that left America's UNIVAC-1 in the dust. For a brief moment, the USSR was ahead in the computing race. But then everything collapsed, and the reason had nothing to do with engineering brilliance. While IBM was mass-producing thousands of computers with standardized parts and assembly lines, Soviet machines were essentially handcrafted. Each computer required scarce components, manual assembly, and expertise that couldn't scale. Universities and research institutions watched helplessly as computing power remained locked inside government laboratories. Enter Nikolai Brusentsov, an engineer at Moscow State University, who refused to accept defeat. He faced an impossible problem. His team needed computers for education and research, but binary mainframes were prohibitively expensive and politically inaccessible. Most engineers would have given up. Brusentsov decided to build something completely different, the mathematician who saw another dimension. Months of frustration led Brusentsov to Sergei Sobolev, a mathematician exploring ideas that seemed almost heretical. Sobolev wasn't working with zeros and ones. He was working with 3 states, -1, 0, and +1. Ternary mathematics. Imagine discovering that color exists when everyone has only ever seen black and white. That's what this moment represented. Suddenly, an entire dimension of possibility opened up. Brusentsov had an epiphany. What if binary logic was never inevitable? What if it was just a historical accident? Early computers used relays and vacuum tubes, devices that naturally had 2 states, on or off. So engineers built systems around those 2 states, and everyone who came after simply accepted it as gospel. But Brusentsov asked the dangerous question, why? Why limit computing to 2 when 3 is possible? Building the impossible. The team started working on Seton, naming it after a small river near Moscow State University. This would be the world's first ternary computer. Instead of bits, it used trits, units that could represent 3 states instead of 2. The implications were staggering. Each trit carried more information than a bit. Mathematical operations became simpler. Negative numbers didn't need special sign bits. They were built into the system naturally. Subtraction and addition flowed more elegantly. The circuits themselves were simpler and required fewer components. For 2 years, Brusentsov's team worked relentlessly. In 1958, they unveiled Seton to the world. The following year, production began at the Kazan Mathematical Machines factory. The specifications tell an incredible story. Just 2,000 magnetic elements and 100 germanium transistors. primitive by any standard, yet Setun operated on a fraction of the components required by binary machines. Research papers from the era documented that Setun used approximately 30% fewer parts than equivalent binary computers. The cost? At least 10 times cheaper than contemporary binary machines. The Soviets had achieved something remarkable, a working ternary computer that was simpler, cheaper, and more efficient than anything the West had built. The death of a revolution. About 50 Setun computers were manufactured and distributed to research institutions across the Soviet Union. For a brief moment, ternary computing was real, and then it died. Not because the technology failed, not because the concept was flawed. Setun died because the factory had no interest in scaling production. The Soviet system, for all its achievements, lacked the ecosystem and political will to support this radical innovation. But there was a bigger problem. The rest of the world had already committed to binary, memory architectures, transistor designs, programming languages. The entire computing stack was locked into two states. Ternary computing, no matter how elegant or efficient, couldn't fight against that momentum. Setun faded into obscurity, a footnote in computing history. For decades, it seemed like the story ended there, the crisis that changes everything. Fast forward to today. Artificial intelligence is devouring energy at terrifying rates. Data centers consume electricity like small countries. Power grids strain under the computational demands of training massive neural networks. Computing is hitting a wall, and that wall looks remarkably similar to the one Brusensov faced 70 years ago. Binary computing might not be enough anymore, but now something has changed. Manufacturing technology has advanced exponentially. New semiconductor materials offer possibilities that didn't exist in the 1950s, and one company just proved that ternary computing might finally be ready for its second chance. That company is Huawei, and what they've built is genuinely shocking. The magic of two thresholds. Every transistor in modern computers works like a person's patience. Annoy them a little, nothing happens. Cross the threshold, and boom, reaction. That threshold switching is the foundation of binary logic. One threshold, two states. Simple. But what if a transistor had two thresholds instead of one? Suddenly, there are three clearly distinguishable states. That's the key to unlocking ternary computing. And it's not just theory anymore. Huawei recently released a patent for a ternary chip built on 7nm technology. They've created specialized transistors with dual thresholds that can reliably distinguish between three states. From there, they've rebuilt the entire architecture. Logic gates, memory cells, processing units. Everything redesigned for three-state logic. A ternary memory cell can now store 3 values instead of 2, packing more data into less space. When simple math becomes revolutionary, consider something basic. An AND gate. In binary computing, it's straightforward. 2 inputs, 4 possible combinations. The gate only outputs true when both inputs are true. In ternary computing, things get fascinating. Each input can be -1, 0, or +1. That creates 27 possible combinations. The ternary AND gate returns the lowest value among inputs. If both inputs are +1, the output is +1. Mix in a 0, the output is 0. Include a -1, the output is -1. This simple change creates dramatically higher information density. More gets processed with the same number of input wires. Chip circuits become more compact. Designs become more efficient. According to Huawei's patent, their ternary chip uses 40% fewer devices, consumes 60% less power, and runs 20% faster than equivalent binary chips. Those aren't incremental improvements, those are revolutionary numbers, the trillion-dollar question. Here's where things get really interesting. Training massive neural networks currently costs millions in electricity alone. Ternary chips could potentially slash those energy bills while simultaneously increasing processing speed. In a data center, that could mean cutting power consumption by a third while boosting computational throughput. Sounds too good to be true, right? That's because there's a catch, and it's a big one. The noise problem. Ternary chips occupy a strange middle ground. Digital binary chips use 2 states. Analog chips use infinite states. Ternary chips sit right in between with 3 states. That positioning could be perfect. Enough flexibility without analog's complexity. But distinguishing 3 states is significantly harder than distinguishing 2. Even tiny electrical noise or microscopic manufacturing imperfections can blur the lines between states, causing errors. Building reliable 3-state logic at massive scale is brutally difficult. And there's another challenge. The entire semiconductor ecosystem is built for binary. Software, memory architectures, compilers, development tools. Everything assumes 2 states. That was Setun's challenge in 1958, and it hasn't disappeared. The carbon revolution. The solution might come from an unexpected place: carbon nanotubes and graphene. These are rolled-up sheets of graphene just a few nanometers wide, and they're nearly perfect for ternary logic. Here's why. The diameter of a carbon nanotube naturally determines how it switches. By controlling that diameter, engineers can precisely set 3 distinct logic levels. It's like nature designed them specifically for ternary computing. But the advantages go far beyond ternary compatibility. Graphene conducts electricity incredibly fast while consuming minimal power. That translates to cooler processors, longer battery life, and massive energy savings in data centers. Companies like TSMC and IMEC are investing heavily in graphene research, viewing it as one of the strongest candidates for the post-silicon era. Recent research published in IEE journals demonstrated a ternary chip built with carbon nanotube transistors at 32 nanometers. The results? 45% less chip area and 30% less energy consumption for the same AI operations that binary chips perform today. These aren't marginal gains. This is a fundamental leap forward. So here's where the story gets uncomfortable. Everything we've built for 70 years, every processor, every algorithm, every line of code, might be running on the wrong foundation. Not slightly wrong, fundamentally wrong. Nikolai Brusentsov proved it in 1958 with a computer that cost 1/10 the price and used 30% fewer components. The world ignored him, laughed at him even, buried his work in Cold War obscurity while pouring trillions into perfecting a system that was flawed from the start. And now, as data centers burn through power grids and AI costs spiral out of control, companies are frantically rediscovering what a small team in Moscow figured out decades ago. Huawei's ternary chip isn't just another incremental improvement, it's proof that we took the wrong turn 70 years ago and we're only now realizing it. Think about that. The device being used to watch this right now could have been 3 times more efficient, run cooler, last longer, and cost less to manufacture. But it doesn't, because in the race between elegant engineering and mass production won. The question now isn't whether ternary computing works. Brusentsov answered that in 1958.
The question is whether humanity has the courage to admit we've been wrong for 70 years and start over. Because the alternative is continuing down a path that gets more expensive, more power-hungry, and more unsustainable every single day. That computer in the Moscow Museum, it's not a relic of a failed experiment. It's a warning we ignored. And judging by what's happening in labs around the world right now, we're about to find out exactly what that ignorance cost us. The future of computing isn't being invented, it's being remembered. And that might be the most disturbing part of all.